uh, to advanced strength materials. We'll be discussing prediction of strength failure first, and then I'll cover fatigue and then fracture. So that's kind of the steps of this lecture series. And again, this course is really covering advanced strength materials, and it's providing you a fundamental understanding of basically how to design systems for from the structural point of view, where when you apply loads to a system, the internal loads to the system need to be reacted, need to be less than the strength of the material, but those internal loads actually form because of the external loads. What is failure? Failure is a complex and complicated topic. You can apply it to a lot of different problems. So if you want to predict failure of a composite versus failure of a metallic structure or an additive manufactured material, the way you will approach failure for those has a similar way, but the formulas for each of those is very nuanced. In all those cases, you're gonna still do testing in the lab. The approach has not changed. You go and do testing in the labs to kind of get the characteristics of the material from the strength and fracture perspective. Exceeding yield strength is one type of failure issue, and exceeding yield strength can be a problem a lot of times. But a lot of times, it's very difficult to actually make sure it doesn't happen. In those instances, we evaluate yield strength. If it occurs locally, the yielding, you could evaluate it to make sure if there's any. You want to make sure that there's no functional performance issues. You want to make sure that there's enough fatigue life if it's yielding locally. And there's no gross new failure modes being introduced by the yielding. Yielding here means if you go beyond this value of yield strength, then the material behaves inelastic, or there's an amount of permanent deformation that's there. So ideally, you want to be below the yield strength, but there are a lot of cases where that's very difficult to avoid. Fracture, it is the separation of a material. So a new cracked surface has formed, new surfaces are formed under loading conditions. Exceeding the ultimate strength, that'll be like a brittle fracture and a ductile fracture. And then fatigue, uh, apologize. Sorry, I've been getting over a cold. The fatigue is application of multiple cycles. I'll be covering both of these topics today as well. Excessive linear elastic deformation, where you have quite a bit of non-linear behavior. And then finally, instability and buckling. I have a whole lecture series in YouTube that covers buckling, so I'm not going to cover it as part of this course. But if you're interested, you can pull it up. The failure of a material can be looked at from several perspectives. So, for example, here what you have is a stress strain curve of the material, and what you also notice is that the stress strain curve provides you few information. It has a yield point of the material, and it has a rupture stress of the material. And in this lecture, what we're going to show you is how to develop the failure criteria of solid materials when they're subjected to multi-axial loading conditions. Okay, and usually when you do when you apply failure criteria of the solid materials and they're subjected to multi-axial stress states, the way we predict failure is based on the results of the uniaxial test. So we're going to use a uniaxial test to inform what the multi-axial loading criteria is going to look like. And I'll give an example of how to deal with that. But what you see here is a uniaxial load, really. So here you have a tension test where the loading is applied, and this is going to help us inform how to deal with multi-axial stress states. There are three widely used inelastic or three widely used materials failure criteria. The first one is maximum shearing stress criterion, and that's good for ductile responses. Then you have the maximum distortion energy theory, and that's the one that's also connected to ductile responses, von Mises. And then finally, we have maximum principal stress, which is really intended for brittle responses. The fatigue from metals will be covered in also later on, and I'll be covering some of that later. But here, what you're looking for is when the system fails at a particular strength level and how to deal with multi-axial loading conditions. So let me cover the first one first, which is the Tresca criterion. The Tresca criterion predicts yielding. The yielding will be initiated when the maximum shear stress in the material equals the maximum shear stress at yielding under uniaxial tension test. Let me repeat one more time because there's a lot of wording here, but the idea is that yielding will initiate when the maximum shear stress in the material equals the maximum shear stress at yielding under uniaxial tension test. So what you see here is there's two parts of the problem. The first part can be divided into before the equals and then after the equals. After the equals, when you apply uniaxial tension test, it is possible to calculate the maximum shear stress. And then before the equal there, you can calculate the maximum shear stress for any material on any multi-axial condition. Under the general state of stress, the maximum shear stress can be found using the principal stresses. We learned about how to do that. And I'm going to go straight to the criteria, not waste any of your time. Very easy. The maximum shear stress can be calculated as the max. So if you had a stress state and you calculated the principal stresses for the material at every point in the body, you can then calculate the difference of two of the components at a time, divide that by two, and then choose the maximum of all of them, and that's your maximum shear stress. That's how you calculate maximum shear stress. You basically subtract two components at a time to get to that answer. Okay, so that's very important. You know, again, two principal stresses. If I have three principal stresses, take two of them, subtract, divide by two, take two of them, divide by two, subtract, take sigma 1 and sigma 3, subtract, divided by 2, and then you take the maximum of all of them, and then that's your max shear stress. So that's the one for a general state of stress. So like if you had a turbine blade or some pressure vessel, that's the calculation you will do. And then you will let the shear stress calculated for uniaxial tension. But it turns out that on the uniaxial tension, the only stress you're applying is just the maximum principal stress in one direction because there's no other stress being applied. And as a consequence, you can find what the max shear stress is, which is 1/2 the stress applied at yield. So when yielding occurs. And so all you have to do now is equate the top equation with the bottom equation. And when this equation is equal to the right equation, that's when yielding is predicted to occur. And so what you can do then is apply loading to the structure, increase the loads to the point where the max shear stress due to the problem you're trying to solve is equal to 1/2 the yield of the material, pretty much. So that's how you will deal with this criteria. And the next criteria I want to discuss is called the von Mises yield criteria, also good for ductile materials. Recall that this one is also good for ductile materials, but so is this. And in this theory, failure is predicted, yielding is predicted at any point of the body when the distortion energy per unit volume in a state of stress equals to that associated with yielding in a simple tension test. Very similarly, we try to determine what, in this case, now you're looking at energy. So what is the energy associated with yielding in a simple tension test? You compare that to the energy, the distortion energy per unit volume, but now for a stress state that's combined. And so the way you can do that, the equations are provided here in the most general sense. I already covered von Mises in a different lecture, but that's okay. The important thing is that you have this in mind. So the distortion energy under stress state condition, and I'm not going to derive the equation, but here you have nu, the Poisson ratio is the modulus. You will have the stress states for the whole, for a particular point in the system. So that whole thing is known, so is the strain energy. Then you have the distortion energy on the uniaxial stress state, which can be easily found by looking at this equation. In fact, if you look at this equation, you will notice that if I set sigma y 0 for uniaxial stress state, sigma z 0, you get, they have two of this, 2 sigma xy squared. There's no shear stresses in a uniaxial test. And so you get twice divided by 6 is 3. And in reality, that general stress state now can be equated to the distortion energy in the test that you're going to conduct. And when sigma x reaches sigma yield, that's the surface we're looking at for when failure occurs. I will equate this equation to this equation. E cancels out. 1 plus nu cancels out. Sorry about that again. Still trying to recover here. And you can see that this is equal now to twice the sigma yield squared. So in other words, if I know the yield of the material, let me draw it for you. Stress strain. If I know when the yielding occurs, that number goes here. And then you can calculate this for any structure that you're studying. And you can compare that to this. And if you are exceeding the value of twice sigma yield squared, then yielding is predicted for that general stress state. Any questions so far about Tresca versus von Mises criteria? If there's no questions, I'll continue then. It looks like the material is clear to you then. I can compare the von Mises criterion against the stress yield criteria for plane stress. And when you do that, you realize that the shape looks very similar, pretty much similar. And you can see that this is slightly tighter. So you have this ellipse going over here compared to the right-hand side where it's more sharp. And so the question can become, which is more accurate. I will say that this is the most commonly used in industry. This is less used, but you can see here it doesn't do it looks very similar in nature. So if you are within the boundary of this ellipse, it's not going to yield. But if you're outside of the boundaries of this ellipse, then it could yield. Note here that that point is this point here. So this ellipse actually goes to that point just like it does here. So again, very similar, and you can plot against each other, and you will see that they do look very similar, both of these. Now, maximum principal stress definition, that's more used for brittle materials and what I mean with brittle material versus ductile, let me remind you what that is. Stress strain curve, and it looks like this, and then another material looks like this. So if the material here fails at less than 3% strain, we call that brittle. And then if we have a material that fails at 5% strain, for example, that's ductile. So for brittle materials, the maximum principal stress that exceeds the ultimate strength tends to be what is used as a way of predicting failure. And all you have to do is calculate the maximum principal stress. There's 3 of them, and then just choose the maximum and compare to the ultimate strength of the material. So 3 failure criteria. There are many more out there for composites, but I will be able to, I won't be able to cover all those criteria here because of lack of time. However, I do have YouTube lectures in composites that show you what kind of failure criteria can be used there. There's at least dozens of failure criteria in composites, and you can then look at more complicated theories out there for metals, where the behavior in tension and compression can look different. Again, we won't cover it in this lecture, but you can actually find some videos I put together on those. Here is a quick example of what the maximum principal stress looks like for a multi-axial loading condition. And you can see here that it's a very simple square when you normalize the sigma 2 against ultimate and sigma 1 against ultimate. Again, this is going to be for a situation that you have an isotropic material. For composites, that's not what it will look like necessarily. With that said, I want to thank you for this particular lecture. I'll be moving forward then